Hey everybody, welcome back. Let's try coding up a neural network in Python today using the Keras package. If you don't quite know what a neural network is, I'd kind of recommend watching the first video that I made in this two-part series. It is linked right here on the screen. But if you know what a neural network is, let's jump into it and begin. Try building a simple neural network using Python's Keras package. In order to make things really simple, I'm going to just go through explain what the data is real quick. The data I collected was from Realtor.com about houses for sale in June 2020 in the eastern portion of Loudoun County, Virginia. For our demonstration, the data has already been cleaned, and we're going to say that the mean price was about $520,000. The goal of this neural network will be to see whether the price of a predicted house is above or below the mean price. So right here, I'm just going to start by reading in the data, and I'm going to show you what it looks like. So as you can see right here, we have a few different metrics. We can see the number of bedrooms, the square footage of the house, the year it was built, the number of garages, the amount of full baths, half baths, the lot size, and then whether it's above the mean price or not. So we put this in for the price, but we're going to see if we can predict this just based on these other values, okay? So first I'm going to begin by kind of putting our data set into array form. The neural network can't really take in a pandas data frame. It's not what it's meant for. And then I'm going to partition our data between the x and the y values. So the x are the first 7 rows of this. We have, the bedrooms, the square foot, all of these through lot square foot. These are all our explanatory variables. So I'm going to label that as our x variables. So there's several columns. And the y is just going to be this last column right here. And we're going to be predicting whether it's above or below the mean price. And that will be a binary variable. So now I'm going to normalize the data. Normally when building a neural network, it does a lot better. It helps kind of learning and everything if you normalize it. Don't normalize the y values, only normalize the x. So I'm going to import this pre-processing from sklearn to kind of help me transform our data. As you can see now, we have a bunch of, this is almost, illegible. I mean, this first column was the number of bedrooms right here. So 0.4, you can't have 0.4 bedrooms. So as you can see, the transformation worked. Now I'm going to partition my data into a training, a validation, and a testing data set. This is kind of typical, and these other sets can be helped to kind of evaluate how strong the neural network is. The training is what the neural network is going to train on, and then we can validate and test our data to kind of deem the model adequacy. So I'm going to partition these. There we go. Now I'm going to build the model. So here's where we're going to finally import Keras, okay? So as you can see right here, I'm going to just kind of run, and I'm going to kind of walk through what I'm doing right here. So right here, this first thing right here is the first activation level, our hidden layer, excuse me. I'm going to use the rectified linear unit because a lot of these inputs are all positive real numbers. Number of bedrooms, those are going to be all positive real numbers. The square footage, the lot size, things of that nature. And I'm going to put our input shape as 7 because we have 7 variables we're inputting. However, we're going to be outputting a 0 or 1 because we want a 1 indicating whether it's above the median price and a 0 indicating whether it's below. This is kind of like a probability you can think of. The support is between 0 and 1. So I'm going to use the sigmoid activation function. So I'm just going to kind of run the model real quick. And then I'm going to compile. These are kind of some of the loss functions, binary, cross entropy. This is kind of determining, how to measure the loss because we're only going to have, a binary response. So it's going to measure the loss with respect to that. And then also we're going to take a look at the model accuracy. So I'm going to run that to compile the model. And then that's the number of times we keep throwing data back in to kind of fine tune. I just kind of picked 100 arbitrarily. It's okay to have a large number. It won't do too much. So let's kind of run this thing. So as you can see right here, it's starting off pretty low accuracy, 36%, 37%. The loss is pretty high. But as we start going down and looking at the number of epochs, we're only at 6, 7, 8. We can really start to see, when you're looking at the accuracy, now it's in the 60s, it goes in the 70s, the 80s, it really starts to climb, which is something that we want to see. And I keep going, eventually I'll get down to the final one. Let's see, so 100, the accuracy ended up getting about to an 88%, and that's generally pretty good. This is only our training stuff, and I'll kind of show you the testing stuff, but generally a good rule of thumb when you're working with neural networks, if you're above 95% accuracy, you likely overfit your model. If you're below 80% accuracy, your model didn't really capture enough of the data's variability. So maybe you need to go back and look for some other variables. If you overfit your model, maybe you need to change the proportion of your training and validation set. So right here I'm going to use the testing set to see what it says. So the accuracy of the testing right here is 80%. Okay, so if we look at the model loss, this is a nice down-sloping curve. This is kind of looking at the, the loss is kind of like think about kind of like the error, a metric to measure the errors. And we want to have the validation less than that of the model loss because that indicates that we avoided underfitting. And notice how they're still pretty close together. They're not super far apart, and this kind of indicates that we avoided overfitting. So this is a good sign. We can also look at the model accuracy. Oh, it looks like the validation set did very well. Typically, if the validation set is higher than that of the training set, we likely avoided overfitting. However, the difference still isn't really that big, or maybe 2% difference. That's indicating that we also likely avoided overfitting, which is a good sign. And accuracy, of course, is just a metric. It's kind of a proportion that it gets correct or not. So let's do an example right here. If I want to be able to predict a house with the following characteristics and see whether it's above or below the average price. Let's say the house has 4 bedrooms, 2,500 square feet. It was built in 2001. It's got 2 garage spaces, 3.5 bathrooms, and 3,452 square feet. So this seems like a pretty nice house. Let's see if it's above or below the median amount in Loudoun County. Oh, it's outputting a 1, and the 1 is indicating that it is likely above, or at least the neural network is predicting that it's above the median price. So in summary, Keras is a very easy to use, well-known library for constructing neural networks in Python. It was designed with a user-friendly API with easy to decipher error messages, and this modeling can be done using neural networks, which emulate human pattern recognition skills to analyze large data sets, particularly with nonlinear responses, but it can also sometimes kind of be another option to something as simple as regression. This can kind of capture some of the variability in a different way, and sometimes if you have data that could be modeled using a regression, it can be good to maybe try out both and see what does a better job in kind of constructing a stronger model. So thanks for watching this video. If you have any questions, feel free to drop them in the comments. Thanks. Have a great day, everyone. Toodaloo.